Hi, today we're doing visible light. Visible light waves are the only electromagnetic waves we can see. We see the waves as the colors of the rainbow. Each color has a different wavelength. Red has the longest wavelength and violet has the shortest wavelength. When all the waves are seen together, they make white light. As a full spectrum of visible light travels through a prism, the wavelengths separate into colors of the rainbow. Because each color is a different wavelength, violet has the shortest wavelength and at around 380 nanometers, and red has the longest wavelength at around 700 nanometers. The 7 colors of the rainbow have various wavelengths. Red has a wavelength about 650 nanometers. Orange has a wavelength of about 590 nanometers. Yellow has a wavelength of 570 nanometers. Green has a wavelength of 510 nanometers. Has a wavelength of 475 nanometers. Indigo has a wavelength of 445 nanometers. Violet has a wavelength of 400 nanometers. The RGB colors have a frequency range of between 4 to 7.5 times 10 to the... Oh, did you stop?
No, just froze.
10 to the negative, or 10 to the 14th power hertz.
Just froze.
Okay.
I think it's a recording.
No. Okay. Oh. Okay. So it's gone. Okay. Just keep going. Okay. So my turn. Okay. So the history of visible light. The history all started with Isaac Newton and his experiments. Isaac Newton was one of the main contributors in discovering the ideas and theories behind visible light. He was trying to disprove Grimaldi's wave theory of light. Newton stated that the laws of reflection and refraction could only be explained if light was made of particles. In 1670, Newton proposed and Newton's both at an angle to have the spectrum recomposed back into white light. Newton was trying to prove the wave theory wrong, and he used the failure of the wave theory to prove that the light is made of particles. Newton concluded that light is composed of colored particles. Newton chose 7 colors as a basis of the color spectrum because of the ancient Greek belief. Now on to the uses. There are many uses for visible light. As you can see behind us, yellow, pink, white, blue, orange. With some uses, it's mostly everyday, but it could be also medically, militarily, basically any type of use. And these all help advance the future of technology and elsewhere. And so some examples include the rainbow, a flashlight, an LED light, a light bulb, a CD, which is also an example of refraction, movie projectors, etc. Now on to our problems. Alright, so the question reads, if you can't read it, a water wave has a frequency of 2 Hz and a wavelength of 1.5 meters. What is the speed at which this wave travels? And also the second part is, what is the amount of energy that the wave has at this frequency? So part A, we're trying to find out what is the speed. So the equation is lambda, which is the wavelength, equals speed over the frequency. So to find the velocity or the speed, it's v equals lambda times f, which equals to 1.5 times 2, which equals to 3.0 meters per second. And that's the speed of the wave at that frequency and wavelength. Now, part B. The equation to find the energy is energy equals Planck's constant, which is 6.3 times 10 to the negative 34, which is also equal to HF, yeah. And which is also equal to HC over lambda. So, we have this, so we can just plug this into there. So, it would be 6.3 times 10 to the negative 34 joules per hertz times by the frequency, which is 2, And that gives us to a 1.32 times 10 to the negative 33 joules. So this is the energy at which that wave travels at that frequency. Thank you. And these are our sources. Source 1. Wait, hold on. Let me put this down. Source 1. Source 2. Source 3. Source 4. Source 5. And source 6. We just want to thank Target for letting us present our project here. They don't know it yet, but they're about to find out. So, thank you. And you can click stop because we have to go. Come on. No, I was kidding. I was trying to make it funny.